Yeah, I think everything is ready now. The recording is okay. The data is clear. Okay, if you have any questions, just don't be shy. It's a good moment to ask your questions about lectures, about differential equations, about optimization, anything that sounds difficult to you. So I'm ready to help you.
Yeah, I have a question about optimization. About one strange way to determine whether the point is maximum or minimum. Mm-hmm. Can I explain in some words what's that? So, and I actually did not understand that method. So there was like XY plane, for example, and then like a Cartesian one, yes. And then the point which we are analyzing, we just draw this point in this plane according to its coordinates. Okay. Then from the start, from the point 0, 0, we draw a gradient vector.
From 0, 0 or from
from 0, 0, yeah, the gradient of the point which we analyze.
And could you provide me some specific example of a function, or it was just some abstract function?
Well, it can be, I think, any vector. So.
Okay.
Yeah, and then the perpendicular line is drawn, like through through this point, and if the
0,
point
0.
Yes,
okay.
Yes. And if this point is on the side with the arrow, like now, it is maximum, and otherwise it is minimum. And I did not understand why and whether it is actually valid method, and whether it is it exists or is just some incorrect thing.
I'm thinking. Just for the moment, I don't get the conditions. Okay, we have a point.
There are also some think that it was used in the case when there were I think something with two constraints. I will find the conditions. They are not just simple ones. Let me find.
Okay, so if you have a special problem, then it's better to discuss it. Maybe I don't know the problem. For the general problem, it seems to be invalid reasoning, but probably for the problem at hand, probably for that particular problem, it's okay. Maybe the reason was something like that. So we have one suspicious point. So A is a suspicious point. And for example, we are searching for just a moment. I think that there may be, for some particular functions, the reason may be like if A is a suspicious point, and if something guarantees us that maybe there are some other suspicion. So I cannot imagine the situation in full, but it seems to me that imagine that you have another suspicious point B there, and in that case, for example, let's assume that Weierstrass theorem guarantees us that there is at least one minimum and at least one maximum point, and in that case, I just look at the gradient, and gradient says, "Ooh, the function grows in that direction." So it seems reasonable that if the level curves separates A and B, and Weierstrass theorem guarantees that we should have two extrema, A and B should be extrema, and we are searching for the maximum, then A is a maximum. So in this particular case, this reasoning is valid. So as a general answer without details, my point is that in general, the reasoning you have provided is not valid, but for some particular problem at hand, maybe with specific function to optimize, specific inequalities, and then it may be okay. An example of such situation is the following. I'm searching for a maximum. I have two suspicious points, and I have calculated I have a level curve that separates two suspicious points. And if I'm searching for the maximum, then the only thing I need to choose whether it's A or B, because I have two suspicious points, and Weierstrass theorem guarantees me that some one of them should be the maximum point. And in that case, as I have only two choices, either maximum point is A, either maximum point is B, then it's sufficient to calculate the gradient at 0, 0. But it would be better just you can send a picture in the chat of the text of a problem. That's okay. I'm ready to help you to discuss optimization problems. So my answer is, in general, the reasoning is not valid, but for particular problem considered, probably it's valid. I need more details to discuss the method.
Yeah, it was the case when there were two constraints and two variables, so that the Hessian matrix cannot be applied. But I think it will be easier to solve it graphically. So it could have been valid. Yeah.
Obviously, when you have
yeah.
two variables, my advice is use. That's a very good idea. If you have two variables, even without two constraints, use plots. That's a very good idea. That would be natural. If it's not prohibited, so just using bordered Hessian matrix. So if it's not prohibited, use graphical approach for the two variable case. I completely agree with you.
Yeah, and this method is not general and it's not commonly known.
The problem is that from the explanation, I don't understand it exactly. Where are the inequalities? So are inequalities active at A or not? I don't get enough information. So if you have a copy of the exact text of a problem, then it would be much better.
Yeah, unfortunately, I have only like this fact. I don't have a problem. So yeah, but okay, I get the point that it's better to do it graphically, and this is not. Yeah. Okay, thank you.
Any more questions? So I'm ready to help you to answer all questions from math-related topics, but I need something. Yeah, Vladislav?
Yes, I have a question. It's about a corollary of equilibrium theorem, which I believe we didn't have in lecture, but it's in the lecture notes by Ferguson, which you sent. Can we clarify? It's a short theorem, so if it's appropriate, I would like to have a few comments.
Oh, I don't remember the first theorem so let me just.
It's called the equilibrium theorem.
Okay, just let me look Ferguson. Just a moment, because I can quickly download it, and here we can have. Yeah, I have opened Ferguson because it's freely available on the web.
It's page 12.
Page 12. Equilibrium theorem. I'm on page 10. Okay, so I will copy and send it to the chat to simplify discussion. Okay. So it's here once, and in Zoom chat. Oops. Control V doesn't work. Just a moment, send the file. I need to open it. Oh, where it is, documents, screenshots. Yeah. Okay, and what is the question?
Well, my question is about only if part, so the backwards argument. That why? Well, can you see only if, and then there is an explanation?
Maybe I will send the link. Just a moment, I will send the link to simplify discussion. Jumps. And in that chat, a copy. Yeah, okay. This is page 12 or 13, probably. Yeah.
Yeah, so I don't really get the step which starts the equality of the first and second terms. Yeah, the step which is that the sum can be zero only if each term is zero, and they then write that the term which is in the brackets Cj minus sum yi aij, they say it's not, it's strictly non-negative, so it's non-negative, and I don't really get their explanation. Why?
Why?
Because
every x is non-negative.
Yes, but Cj is the boundary which is set as an inequality when
yi
or yi aij, sum of this y is more than Cj, and so shouldn't it be more than Cj?
Just let us check the statement of okay, every term is just a moment. In a standard minimization problem, we have every y is greater or equal than c.
Yes.
Okay, probably it's a misprint, is non-positive, but
if it's non-positive, then their argument won't work.
Why?
Well, because here they refer to its non-negativity.
No. They use no. Okay, replace non-negative by non-positive. The sum can be zero only if each term is zero. You multiply non-negative numbers by non-positive numbers, you get non-negative numbers, non-positive numbers, and the sum can be zero only if every term is zero. Everything is fine.
Okay, yeah.
So
yeah,
you are right, you have spotted a misprint in Ferguson. You are right that the sum is non-positive, but the argument is still valid. So you are completely right, you have spotted a mistake in the exposition, but the argument is, however, but it can be just a little bit. So you multiply x star j is non-negative, and the difference in brackets is non-positive. So the product is non-positive for zero, and the sum is equal to zero. So the only way is each term is zero, and the following text is valid. Okay, but you're great. So I appreciate your effort, and you have spotted really a mistake. So that's very good. So indeed, C minus sum of y times A is indeed by the standard statement of minimization problem, this difference is negative or 0. Yeah, you're right. I think you may even write to Ferguson because he's very adequate guy, and I think he will correct. He's alive and very friendly, so you can just send him a message, and I think he will correct this point in a text, because basically that's a great text. Okay, thank you very much. Yeah, I completely agree with you, but the argument of Ferguson is still valid.
Okay.
Any more questions? Okay, so let's solve some optimization problems and probably discuss some topics in differential difference equations. Okay, once again, my message. I'm always ready to help you with your difficulties in optimization, differential equations, and so on. And if you just send me something beforehand, it may be a little bit more effective. But once again, do not be shy, and I'm ready to answer your questions. Okay, so let's consider some applied optimization problem, something applied optimization problem. So let's consider some maximum likelihood optimization. I have, you know about maximum likelihood, yeah, from statistics?
Yeah.
Okay, so let's solve some problem like that. You have x1, x2, xn are independent, and they have density function that is that has two unknown parameters. So you have either 0 if x is less than a, and you have something like lambda times exponent of minus lambda times x minus a if x is greater or equal than a. And my question is find lambda hat and a hat by maximum likelihood. Yeah, like that. The problem is clear?
Thank you, it's clear.
Okay, let's first we will quickly work like probabilistic part, and then we have optimization part. Basically, we have two parts. We need to understand probabilistic context of this problem. We need to recall what is a maximum likelihood method. So which function is optimized with respect to which variables, and then we can optimize it. So, okay, first we need to have some probabilistic reasoning, and then we need to have some optimization reasoning. Okay, who remembers the idea of maximum likelihood? What is optimized?
Well, we should multiply densities of each xi, and then maximize.
You're right. You're right. We maximize with respect to parameters. We have two unknown parameters here, a and lambda, and we maximize the joint density of x1, x2, xn. As we have observations, we optimize this joint density, or we maximize, you're right, that this joint density we have, I think that's all from probability theory that we need. And in case of independent variables, our joint density can be represented as what?
Product.
Okay, yeah. So we maximize with respect to A and lambda product from 1 to n, product from 1 to n, f at xi. Yeah. So basically, the probabilistic part of the problem is finished. So we need to, you are completely right, the method of maximum likelihood maximizes the joint density. And in the case when variables are independent, we have equality of joint density to the product of marginal individual densities. Basically, probabilistic part is finished. And now we go to the optimization part. Okay, what will we do? So once
We
again,
can take logger.
f of x is, just a moment, I will copy lambda e minus lambda x minus a if x is greater than a, 0 if x is less than a, and we maximize. So we basically we have no probabilities now. Everything is just so we have no probability theory basically. So probably it's good to keep in mind what we are doing, but basically we will not use probability theory anymore, I think. Yeah, so that's basically optimization problem. Yeah, what we should do about this problem?
I'll take logger.
Yes, you are right, we can. Okay, so what do, so that's a great idea. Why it's a great idea to take logarithm in this situation?
To have sum rather than products.
Okay, yeah. What should I write? What should I do? I should maximize what?
Well, if already taken logs, then it will be n multiplied by lambda.
Sum logarithm of f of xy, yeah? I just replace product by sum, f by logarithm of f. Yes, I agree, you're completely right. So I will maximize with respect to a and b, and what should I write there here?
N multiplied log lambda.
I take sum. Let me write this. It will be the function q of a and lambda. First, let's simplify it. Yeah. Q of a and lambda is sum of logarithm of lambda exponent minus lambda x number I minus a, and you get sum of ln lambda minus lambda sum of xi minus a. Yes, you are right that this does not depend on index. So just n logarithm lambda minus lambda xi minus a. This is my function. Okay, and what should I do next? We got rid of exponent as Stepan advised. Take derivative with respect to what?
Well, we need to find two.
We need to find both estimators. Okay, so dq d lambda is n over lambda minus sum of xi minus a. D Q d lambda is
But why the lambda again?
oh sorry dA is
So it's minus lambda multiplied by n.
I think it's plus
Yeah,
plus n lambda. What else? You I think you are starting to see the problem. That's not so easy. It's a trap. Yeah. Can you spot the trap?
Oh yeah, we
Something
get just number.
is not okay. Yeah, because if I try to just say something like n over lambda hat minus sum of xi minus a hat equals to 0, it seems okay. Then the second equation seems okay. And oops, obviously there are no solutions, because from the second equation we need lambda hat is equal to 0, and from the first equation we cannot have lambda estimator of lambda equal to 0. Okay, no solutions. Okay, that's not so easy. So that was a that's why I have decided to consider this problem, because it seems a little bit it's a good trap. Where is the trap? What we have done wrong? Or there are no, so probably there are some cases then, so probably there are some models in statistics where maximum likelihood estimators do not exist. That may happen. Honestly, if you look at even at a simple logistic model, I don't know whether you know about logistic model or not. Have you heard about logistic model? Okay, I have. Okay, thank you, Stepan. Thank you for being active. That's great. First point that there are some, what we should know, there are some models in statistics where maximum likelihood estimators do not exist. So first, general idea that there are some models in statistics where the maximum likelihood estimator does not exist. But that's not the case. The trap is that we have done something wrong during optimization. So, but that's not the case. In this particular problem, maximize the joint density of this particular type. It was our mistake that I deliberately allowed you to do. So I know where is the mistake. We have done a small, very intricate, let's say, mistake. So if we will do optimization correctly, then we will find the maximum likelihood estimators in that case. So, but in this case, lambda hat and a hat do exist. So we have just done a mistake. Who can spot the mistake? So we have done everything correctly in probabilistic part. So indeed, it's a correct translation of maximum likelihood to optimization problem. Indeed, we need to take the product of all marginal densities. We need to multiply them, and we need to maximize them with respect to two parameters. A and lambda. That is perfectly correct. The mistake is not on the previous page, so mistake is somewhere here.
Oh, we have constraints which we need to consider. Yeah.
Constraints, in some way you are right that we have constraints. Obviously, lambda cannot be 0 or negative. Yeah, we have constraints. That's a good idea to think about constraints. Let's write them. Constraints, hidden constraints. There, yeah, that's a good idea to speak about hidden constraints. What is a constraint on lambda and what is a constraint on A?
Well, lambda is positive, and
Yeah, lambda is strictly positive. Okay.
A should be less or equal than minimum value.
So first, let's start from the constraints on the problem. So we need to separate. So as we have fallen into a trap, so let's be very careful. Let's distinguish about. Let's distinguish exogenous constraints and indigenous constraints. So we need to be very careful for that problem. So in the beginning of the problem, we have no limit for A. So as a result of optimization, you're probably right. But first, let's discuss exogenous constraint. What is the possible value for parameters A? A is any number. And as a result of optimization, you probably can get the result you want. But in this function will be, so what is the meaning of parameter A? A parameter A is a shift parameter. It will shift the distribution. And we have, probably we can shift distribution to the right, probably we can shift distribution to the left. So I will just distinguish what you are saying, Stepan, is right. A in that sense, but it's a result of optimization. And I'd like to be very accurate, clear. So these are exogenous constraints. When I solve the problem, this is a density function. It looks like, let me draw this function probably, f of x, and it's 0. And oops, it jumps. It jumps and then decreases, and the jump point is A. And there are no exogenous restrictions on A. A may be negative, yeah, maybe my observed x1, x2 are from -5 up to +infinity. But you're right, Stepan. I appreciate your point. When we what is the subtle error we have done? The subtle error is here. We have implicitly assumed that the logarithm exists. And that's not always the case. For example, you are right that when x is less than A, this expression is okay, it's 0. We multiply 0 by something. And when we go from maximization of product into optimization of sum of logarithms, that can be done in many cases, but not always. And that's exactly here the trap is located. Yeah, here is the trap. That's the first step is a mistake, because we can take logarithm when we are sure then the expression is greater than 0. And in our case, there are two possible values, 0 and so basically what we can do, why do you write that A is greater than minimum of x1, x2, and so on? Stepan, what's your reasoning behind that A is greater than minimum?
Well, I think it should be less than minimum.
Why? Greater, less? What's the
Uh,
reason?
because otherwise we will multiply all densities and we will get 0, which is just the result we do not need.
Yeah, I
Because
agree.
we can obtain the multiplication which results in the value higher than 0.
Yeah, I completely agree with you. So I will do now a correct solution. I would prefer on the next page. On the next page. So the correct implementation. So the idea is right. We need to multiply density functions, but we can get 0 if at least one of the terms is 0. So the Q, so before logarithm, so let's let's call lnq, lnq. That's better, I think, like that. Okay, so in my cases, if I will write my function q before taking logarithms with all conditions, then it will be equal to lambda to the power n times exponent of minus lambda x1 minus a times exponent of minus lambda x2 minus a, and so on. And the first line, and 0 otherwise, and the first line will work if x1 is greater than a, x2 is greater than a, and so on. And the second line will work if at least one of x1, xn is strictly less than a. So that's the correct full expression for my goal function q. Indeed, it's a product of individual densities, but sometimes this product is 0. And now you're right that we can write this condition as if every x1 is so the condition x1 is greater than a, x2 is greater than a, xn is greater than a, it's exactly the condition that minimum of x1 xn is greater than a. If every x is greater than a, then the minimal x is greater than a. If minimal x is greater than a, then every x is greater than a. So indeed, it's a necessary and sufficient condition to work with first line and not the second, not the 0. And obviously, when we minimize, we would prefer even a small positive number to 0. Our goal is to maximize q. So even 1/million is better than 0. Even 1/10 million is better than 0. Our goal is to maximize, and so we can conclude that to have a positive q, we need to have a hat should be less or equal to minimum of x1, xn. Okay.
Yes.
Because otherwise we obtain 0 as optimization result, and it's not our goal. Okay, and basically let us simplify once again expression q. So we are maximizing by lambda and a, given that a is less than, we can now incorporate. So there were no such restriction in original problem, but we can incorporate it since we know that the optimal point a cannot be greater than minimum, because if a is greater than minimum, that our value is 0, and we would prefer any positive epsilon 1/million, 1/trillion to this 0. So we can incorporate this inequality into our optimization problem. So a is less than minimum of x1, xn. We optimize the same function, but if this condition is satisfied, then we can work with first line. And first line says maximize lambda to the power n exponent of minus lambda times sum of xi minus a. So that's a that's basically the error. It seems at first glance that we have unconditional problem, but when we take log and when we forget about 0, then we have transformed our problem from unconditional optimization to conditional optimization. It's very strange. Wow. But to have, we prefer to have positive number than to have 0. And to work with positive numbers, we need to add one restriction. And so the trap was that we missed a restriction. So we cannot just take derivative and with respect to a and make it equal to 0, because we have inequality problem. But now you are right that we can take logarithms. So our goal is to maximize n logarithm lambda minus lambda sum of xa minus a with respect to lambda a and the hidden but now visible inequality that a is less than minimum of x1, xn. So that's a correct statement of our problem. Any questions?
No.
Okay, we can, there are many ways we can do it. We can, for example, introduce, and why I ignore this, so one more question. And why I ignore condition lambda greater than 0? Why I'm ignoring it? It's also an inequality. Why I'm ignoring? The right answer is that only non-strict inequalities are important when we do optimization, because strict inequalities, they, in general, they describe open sets, and all our optimization techniques, they basically ask us about whether we are on the border or not on the border. So conditions are different when some condition is active and when some condition is not active. The condition lambda is greater than 0 can never be active. So I may safely ignore, so as condition may never be active, d function with respect to d lambda should be 0. This condition is never active. And if condition is never active, then the only possibility to satisfy it is to have dl d lambda is exactly equal to 0. Okay.
Okay.
So I'm ignoring it because the first order conditions are like are exactly like without this condition. That's why I'm ignoring it. If I will obtain negative lambda, I will say, oops, there are no solutions. If I obtain positive lambda, I will say, oh, there is a solution. But I will not introduce Lagrange multiplier for lambda. Okay, let's move on. I can introduce something like Lagrangian function, like so it is approach one. Approach one. It's n ln lambda minus lambda sum of I minus a plus some mu times minimum x1 xn minus a. So I may work with a Lagrange multiplier method, but the problem is that we have a non-differentiable condition. Yeah, our inequality is not differentiable, so it cannot be applied non-differentiable function. So Lagrange multiplier approach fails here, and we just need to switch on our general reasoning and logic. Let's look at this function. We see that lambda enters this function in a very intricate way. We have logarithm of lambda minus lambda, but a is just multiplied by plus lambda. So we see that basically, if I transform once again my function, I need to maximize with respect to lambda. A is less than minimum of x1 xn, and I'm maximizing n ln lambda minus lambda sum of xa plus n lambda a. And I perfectly see that my function grows linearly with a. The bigger is a, the bigger is my function. So what is the optimal a? What is the a optimal? It's very easy to find the optimal a in that situation.
It's minimum of x.
I would like to prefer the biggest a as possible. Yeah, I would like to prefer the biggest value of a as possible, but it's impossible to have a bigger than minimum. So we have already found one point. It's minimum of x1, x2, xn. So bingo, we have done half of the problem. Yeah, that's half of the problem.
Yes.
Okay, and now what else? I think the second half of the problem is much easier. Sorry, I haven't understood. I have understood nothing. Probably
yes.
it was.
Can you hear me?
Yeah.
What if we had strict inequality?
Okay, let's discuss what will happen if we have a question. What if we have maximize with respect to lambda, a is less than minimum, and the function is the same? Yeah, it's your question, because I have a lot of noise on the voice channel. Am I right about your question? I don't see you. Could you write in chat whether I have understood your question right? Lambda. Okay. So in that case, the answer is easy. So no global or local constraint optimal. So in this case, when you would like to make the function as big as possible, but you have a strict inequality. In that case, that's a correct problem, but the answer for this problem, no global extrema in that case. So that's a good question. What if? I like very much what if type of questions because they foster our curiosity, and I like very much this type of question. Thank you, Vladislav. But unfortunately, the answer for your question is oops. In that case, in that case, there are no ML estimators. Yeah. If you have such a restriction, but we, in our problem, yeah, there may be. You are exactly right in that sense. That exactly, maybe not exactly. Yeah, exactly this phenomenon happens in logic models when we are trying to forecast with maximum likelihood binary variables. And this is exactly the reason why in stats models in Python, there is a default regularization in logic models. So basically, yes, there are some cases when maximum likelihood estimators do not exist, and we need to do something in that cases. And the standard decision is to penalize maximum likelihood function for big values of parameters. So in that case, some penalty is provided, something like that's so in our case, we would like to make A as close as possible to minimum. Okay, let's penalize our function. Let's add some penalty, but in that case, the maximum likelihood estimator will not exist. Okay, let's go back to our original problem. Yeah.
Sorry, could I have a question?
Yeah.
We don't have a maximum likelihood for only A or for lambda too?
Or
I mean, I think we can estimate still lambda, or it's not even possible.
No, you cannot estimate lambda. What will be the value of lambda if we, or you mean that if you consider modified problem? So what if, so if you consider original problem, so if you are asking another what if question, if you have maximize with respect to lambda n ln lambda minus lambda xi plus n lambda a, and a is fixed, then indeed you are right. You can estimate for fixed value of a, you can obviously find maximum likelihood estimator for lambda.
But in that case, which is a little bit above, we cannot estimate lambda, yeah?
So let's mark them Q1. So it will be Q1 and it will be Q2.
Yeah, in
Q1
case.
situation, in Q1 case, you have two unknown parameters, and as you cannot maximize with respect to one of them, so oops, there are no global extrema.
What I mean is, it's not our target to maximize first of all, but to find the best estimator, which could serve as much big value of this function could have.
We call estimator now is a vector. So from a theoretical point of view, theta, the unknown parameter now is a vector, is like lambda and a. And in this case, the vector theta of unknown parameters is just lambda. And in that case, the vector in Q1 case, the vector fails to exist. Yes, the problem is in A, but we are searching for the vector of unknown parameters, so our search failed. Yes, it failed for the reason of non-finding A, but it failed. And in Q2, you are right that in second situation, if A is fixed and given, you know by some other estimation method, I don't know, maybe a method of moment or any other method, you know that I have estimated A as 5, and then I use maximum likelihood to estimate lambda given A, and it exists. Yeah.
Okay, thank you.
So you are right in the sense that the problem, our problem is an estimation of A. But if our original goal is to estimate both, then we cannot, yes, exactly for the reason of A. Okay, but now we can, because our situation is not what if. Be careful, in our original problem, A is less or equal than minimum. And in our case, we can easily find the maximum likelihood estimator because we maximize monotonic function. And obviously, the maximum of monotonic function is on the border. The border is A equal to minimum. And what is left? What is left is optimization with respect to lambda. We can plug in, so we can plug in A in our function. And so we now maximize with respect to lambda and ln lambda minus lambda sum of xi minus minimum of x1 xn. And here we have no problems with derivative, with logarithm, so we can just indeed find the derivative. That's not a problem. If we will know this function as q small of lambda, then q prime is n over lambda minus sum of xi minus minimum of x1 xn. Q prime prime second derivative is minus n over lambda squared. And in that case, we have no technical problems to optimize. Yeah, or maybe I should go on the next page. I think it's not visible on the bottom. Just 1 minute. We will finish our big problem with indigenous inequality condition. So we go back to our original problem. We have that A original problem. A is a minimum of x1, xn, and we maximize with respect to lambda and a logarithm of lambda minus lambda sum of xi minus minimum. Ooh, it's a little bit boring now. I will denote my function by q of lambda. Q prime is n over lambda minus sum xi minus minimum x1 xn. And I think we have done everything in our case. This is the value of lambda hat. So lambda hat is just n divided by sum of xi minus n times minimum of x1 xn. We see that q prime prime second derivative is negative. So this point is indeed maximum. And basically we have the answer.
Excuse me, and which problem we have with maximization of function with which was non-differentiable in the beginning when we have constraint? Because this one L.
Yeah, you are right that we maximize. Yeah, you are right. Yeah, you are right. I'm wrong. Yeah, exactly. You are right. That's it's non-differentiable with respect. Yeah, you're completely right. That's my fault. Yeah, you're completely right. It's non-differentiable, but it's non-differentiable with respect to what? Yeah, you're completely right. It's non-differentiable with respect to what?
To x1, x.
Yeah, with respect to x1, x2, and we are optimizing with respect to
lambda and a.
Yeah. So we can use it, but okay, non-differentiable function with respect to x1, xn, but we do not care. Yeah, you're right. That was my fault. We can use Lagrangian multiplier approach here. You are completely right. Thank you very much. But our solution is also fine. Any questions? Yeah, you're completely right. Thank you very much. So I just think, oh, it's non-differentiable, and I think, oh, that's use another approach. Okay, so our final answer is A is equal to minimum of the vector x, and lambda hat is equal to n times sum of x minus n times minimum of x. And I think it's a good example of optimization problem. Okay, any questions?
Thank you. No
Yeah.
question.
Okay, let's move on to, we have, I think, 10 minutes. Let's solve some, I think, difference equations. Let's solve some difference equations, like, example, let's solve like yt plus 1 minus, I don't care, 2yt equals to 7 and y0 is 3. Let's solve some difference equation. I think 10 minutes is enough for that problem. How can we solve it?
And first solve homogeneous one, and then like find the particular integral and combine.
Yeah, you're right. That's a standard solution. Basically, you can solve this problem even without any topics studied in the university. Basically, this problem can be solved by a person who knows about geometric progressions. So basically, there is school level, middle school, yeah, not the high school, but middle school level solution. How we can solve it without words like homogeneous function, characteristic equation. I'm scared. I'm a schoolboy. I'd like to have something that's easy.
Just insert value which you already know, then try is there any kind of answers.
Sorry?
I mean, the simple middle school level solution, just use the number we already have. Try to, is there any kind of way to find a solution? I mean, Stefan have answer. Let's see his answer.
Answer. Okay, basically, yes, you have like something like try and guess a solution that will copy as middle school, just input the value you already have to try and yeah, we may just by induction. Yes, we can use induction, so we can say that what is y1 is will be 7 plus 2 by 3, and y2 will be 7 plus 2 times 7 plus 2 by 3, and y3 will be 7 plus 2 times 7 plus 2 plus 7 plus 2 times 3. Yeah, I think yes. And how can we spot the pattern? Okay, so first idea how I will solve it at the school level. First idea, obviously at school level, I will get, without 7. So basically the school idea is just to say, yeah, I can solve something like that. I can easily solve something like that because it's a geometric progression. Oh, I know that yt plus 1 is 2 yt, so yt plus 1 is y0 times q times 2 to the power t plus 1. Okay, so this I know how to solve because I have studied geometric progressions. And now the main idea, I'd like to kill 7, but I'm in school, so I cannot do like university guys. I cannot just say, I will solve without 7. I will obtain what is known as the homogeneous solution. I will find a particular solution. That's too hard for me. I'm not enough brave to just remove 7. But I'm brave enough. The part will change, will become the part to multiply in the next time by 2. Yes, you are right in that sense. I'm not too brave to completely remove 7, but I'm brave enough to move 7 to the left-hand side. And that is okay for my school level of understanding. Without these characteristic equations, lambdas, and so on, I can just move 7 to the left-hand side, yt plus 1 minus 2yt minus 7 is 0. So the right-hand side is okay. And now, what will I do? I can move this 7. I can move this 7 partly into yt and partly into yt plus 1. So imagine that I subtract, imagine that I add something plus something to yt plus 1. Yeah, if I add something to yt plus 1 and add something to yt, I will get exactly the same number subtracted. So if I do something like the coefficients are 1 and minus 2, and I might say that it's 1 yt plus 1 minus 2 yt plus 1 minus 2 times 7, yeah? And I see exactly that it's yt plus 1 plus 7 minus 2 yt plus 7, and it's 0. And that's enough for me to solve this example at middle school level, yeah? I can just say that I work with the second sequence ZT, that is yt plus 7, And the equation for zt is zt plus 1 minus 2zt is 0. So I immediately obtain this. I recognize this equation as a geometric progression. So zt is equal to z0 plus multiply times 2 to the power t. And yt is zt minus 7. And basically, bingo, I have solved without any ugly words like characteristic equation. I have yt, that is some constant z0 times 2 to the power of t minus 7. And I'm happy with basically middle school methods. Okay, any questions? I forgot initial condition. Yeah, I forgot. Sorry, I forgot initial condition. Y0 is 3. But I think you can finish it, yeah? So if y0 is 3, then it happens to z0 times 2, 0 minus 7 is 3. And basically, z0 is, I think, 4. Yeah, 4 minus
I think 10.
10. Yeah, you're right. I'm wrong. Yeah, be careful because I can do mistakes. And finally, my final answer is 10 to the power t minus 7. Basically, this trick works for first order difference equations. And it's funny that we can solve it very fast. And even that may be a motivation for introduction of characteristic equations. That's all for today. If you have any questions, don't be shy. Write me your question and we can certainly discuss it. I'm ready to help.
So what if t equals to 0?
Sorry?
So it just means, I mean, I type in our chat. If t equals to 0, so what happened?
What happened? If t is 0, yt will be 4. 10 minus 7 will be 3. Yeah, it should be 3. If t is 0, then we should have 3. If t is 0, we will have 3 in our formula. That's okay.
Okay, got it. Thank you.
Okay, bye-bye.
Bye-bye, Boris. See you after.
Thank you, goodbye.